Hi there and welcome to another short web snippet brought to you by the guys here at Innova Systems. My name's Matthew and this time I'm going to be talking to you a little bit about using SolidWorks Simulation Professional to study an electronics cooling enclosure. Okay, so first of all let's kick off by considering the problem that we've got in hand. So what we've got here is a simple electronics enclosure, and what we're going to be looking at trying to do is examine the temperature distribution within our enclosure. The objective of our analysis: to ensure that the microchips that we've got within our enclosure stay below their maximum operating temperature of, in this case, 90 degrees C. The idea is that we don't want them failing during operation. And how are we going to achieve this? Well, we've got a heat sink attached to the bottom of the enclosure, and we're going to try and optimize that design by making a few changes. So let's have a look. Now what you'll see we've got here is a very simple geometry. We've got our enclosure. We've got our 1060 alloy base plates. We haven't got any cooling fins on the bottom just yet, but we will be making those sorts of design changes shortly. And we've got a couple of standoffs which are just used for mounting the PCB. So you'll see the PCB sits just atop those standoffs. Then we've got the chips on top of that PCB. And finally we've got the outer enclosure. Okay, so let's have a look at our first study. One thing I'll draw your attention to is the fact that I've already assigned my materials to each of the components in here. We've got the copper PCB mix. The reason I've used a copper mix is because the thermal properties of our PCB are very specific, so I've just created my own material and spliced a couple of the thermal properties of the standard PCB FR4 plastic and some of the copper. We've also got the material of our base plate, our cover, the chips, and you'll also notice I've got a solid body in here which is filling the entire internal volume of air with a solid, and then I've specified for that volume to be made from air. This reduces the complexity of our system by, instead of relying upon convection coefficients etc. inside the material, we can just assume that our air body is conducting heat away from each of the other bodies within the model. We've got our heat power emanating from each of the chips. We've got 4 watts of heat power being generated by each of those chips. And then finally I've applied a convection coefficient of about 5 watts per square meter per Kelvin to all of the external exposed faces. And that replicates an open environment in which we haven't got any forced cooling, it's just natural still air. Okay, so let's have a look at our thermal results now. What you'll see is I've got a maximum temperature annotation of 101 degrees at the moment. We can't really see what that's on, so we'll use a couple of other techniques to have a look inside our enclosure. First of all, we can use the ISO clipping, which is a tool that allows us to drag a slider through our temperature values and isolate any values above our certain temperature. So we can just see those higher temperatures in this case here. You'll notice that our maximum temperature annotation is actually on one of the chips. So in this case, our design has failed to meet our criteria. One tool which I think is probably going to be more useful for us here is our section clipping tool. And that gives us a plane which we can drag through our model to have a look at the cross section, have a look inside that enclosure housing. If I just switch this plane to the right plane, we've got a nice view inside the geometry there. Okay, so now let's have a look at starting to make some changes. The first thing I'm going to do is switch to our standoffs configuration. So you'll see here now we've added some standoffs underneath where the chips are on the PCB. Hopefully they're going to draw some of the temperature away from the chips themselves. So now you'll notice with this thermal result, we've got a maximum temperature of 93.8 degrees. So that design change has reduced our maximum temperature, but we still haven't managed to bring it within our design criteria. These chips would still be failing in this case. So let's have a look at making another change now. And we're going to start by adding some fins on the underside of that heatsink. So if I rotate round, you'll see that we've got some short fins that span just across the distance of the microchips on the underside of the heatsink. And the idea of those fins is to increase the surface area of our heatsink, which increases its ability to lose heat to our environment. Okay, so now let's have a look at the results that we've got using our fins. You'll see now we've managed to bring that maximum temperature on the microchip down to 86 degrees. So we have now brought the design within our criteria, and we wouldn't be expecting to see these chips fail at this exact situation. Obviously, there is some variation in the environment which might cause the overall temperature to be elevated by a couple of degrees, which might still knock us into a failure. So let's have a look at improving that fin design. So now you'll see on the bottom here, I've got fins spanning across the entire length of the underside of that heatsink. Let's have a look how that makes a difference. Okay, now you'll see we've brought our maximum temperature on that chip down to 79.9 degrees. So we are well below that maximum operating temperature now. So any external environment fluctuations in temperature will have less of a significant impact on our chips and will be much less likely to cause a failure. Now, one thing I would like to show you before we come to a close is another option that we have available to us in SolidWorks Simulation Professional, and that's the opportunity to examine transient responses. So with our thermal study, what we can do is have a look at how the temperature varies with respect to time. Having a look inside the study properties, you'll see that I've specified a total time of 18,000 seconds with a time increment of 150 seconds. That's just the increment in which results will be saved out, so we can have a look at each of those time steps. You'll also notice that after our 18,000 seconds, we've got the same maximum temperature, and therefore we've reached our steady state situation like we had in the previous study. The key thing that we have available to us here, if I use the probe tool and just grab a node from the surface of one of these chips, you'll notice that we've got this response button appear now. If I click that, you'll see we get our time response curve. So this is how the temperature varied at that node across the entire time history of our study. So you'll see we've got an initial increase up to about 70 degrees, where we have a plateau which indicates that we've reached that steady situation. So our steady state situation seems to occur at about 7,300 seconds. Okay, so in summary, why have we used SolidWorks Simulation Professional in this case? Well, we've used it to examine the temperature distribution within our parts. And it's also helped us to understand how our changes to the design have affected the thermal efficiency. It's also become a very good tool for helping us maximize the cooling, but at the same time minimize the material usage and therefore cost. And this increase in efficiency also has the effect of helping us to protect our sensitive components. And that's about all I've got time for, so thank you for joining me. As always, if you wanted to get in touch, you can visit our website, which is www.innova-systems.co.uk. You can drop us an email at support@innova-systems.co.uk, or you can call us on the number you see on your screen now.